So we've been making really good progress with our rules for differentiation, and we even looked at, how the process of differentiation can be repeated, again, because it's just so much fun. Well, as far as like the basic rules that involve operations like addition, subtraction, multiplication, division, we have those covered. But there's another operation that's very unique to functions, right? And it's often one that requires a little bit more thought and a little bit more care. And it's called the chain rule, although the name doesn't. I don't think the name does it. It doesn't serve any clear indication of what the operation really is. And I would love it if we could change the name of the chain rule and maybe call it the composite rule, because that's really when you use it, right? And speaking of the composite, I just want to quickly review the idea of the composite of two functions, because if that concept is not fully understood, then it makes it very difficult to understand when and how to use this particular rule, right? And in fact, let me do something that's, you may have already been exposed to this idea, but I think when if you limit your understanding of a function just to equations, I think you're losing sight of something bigger, right? A function isn't just an equation. A function is it's something. It is a process. It does something, right? And it shows how things are related. So, for instance, so let's say you start with a number x, and you plug that X into a magical box. And it's somehow this X is transformed. It's like, like the before and after. And let's say this magical box just happens to be called F, right? Well, you plug something into this function, and again, something is going to appear on the other side. And we just happen to call it f of x, right? It could be something else, right? But the thing is, what's most important about this is that you have an input. This is like the before. And then you have this magic box that does something to your input. And then it produces an output, right? So specifically, the X represents the input that goes into F. And then F of X represents the output from F, right? And that's really what a function is. It could be an equation. It could be something else. It could be some other type of process. Here's another example. Like when you touch the screen on your smartphone, and they're so smart now, they know that you have different pressures that you can apply. So if you use a light pressure, it does one thing. If you do a harder pressure, it does something else. That's an input and that's an output. You touch the different keys on your keyboard, you get a different response. All those are examples of functions. So functions go well beyond just a math course, but a math course is what it makes everything formal, and once you understand it, you see how it relates to everything around you, right? Well, what do we mean by a composite? Well, suppose you have more than one function. Suppose the output that you get from f, you decide to plug it into another function. Suppose there's another magical box, right? and it does something different from f, so let's give it a different name, right, to represent the different thing that it does. Well, let's call it g. So what was the output from f now becomes the input into g. So it leaves one function and it goes into another one. And then if we want to continue using this notation, just like how I took this input and it went into this function and I labeled the output like this, then I better, for consistency, and that way everyone understands what's going on, I better use the same notation for this. So then it would have to be, what comes out of the second box here would be g of f of x, right? And then so this now would be the output from g, right? And then you could say, well, what if this goes into another process? So like this whole idea, this whole chain of functions, which is in part kind of where the name comes from. Think about what happens on an assembly line, right? Think about what happens on an assembly line where you start with a raw material or something, and then a part of the process you do something to it. Maybe you sanitize it, you get it clean. That's all this function does. It just cleans things. And then it takes the cleaned item and then it does something else. Maybe it starts to mold it in a particular form, or maybe this one cuts it into smaller pieces, and then that output goes somewhere else. So you could have a whole chain of these functions, and all they do is they take an input and they produce an output. All right? And notice I never wrote an equal sign anywhere. There's no equal sign in any of this, right? It's bigger than just an equation. All right? But of course, we have to bring it back to equations. Equations and everything associated with algebra plays such a big role in this particular course, right? Well, so what does this look like? Well, normally we use, either y or the f of x. So it would be a situation where, let's say we have an x. And then what you're going to do is your function now, like your f of x might be x squared minus 3x plus 1, right? And that's what would come out of this particular function. If you plug your x in, it's going to do this, and then you're going to get out your x squared minus 3x plus 1. But then suppose you had another function now that was like a square root, right? So you had a root. Well, what it would do, it would say, whatever you plug into me, I'm going to take the square root of it. So then it would produce the square root of this expression, x squared minus 3x plus 1. And this is what we need to get used to now. And I think we are. It's just a matter, we're going to see this type of expression a lot. So we refer to this as the composite of this function with this function, right? So this is the composite of these two functions. And let's use a regular, function notation, or y equals notation. So y equals x squared minus 3x plus 1, and this other function, the square root of x, right? So the composite is another way for us to take two functions and create a third, right? Or to take three individual functions and create a fourth, right? And what we want to be able to do is to find the derivative of these types of functions, all right? And that's where the chain rule comes in. Now, the chain rule is the only rule that I am not going to use the limit definition, because it gets messy. The proof is truly beyond the scope of what you normally do in your first semester of calculus. However, that's not to say I can't at least give you an intuition as to where or why the formula works out this way, right? So we're going to state there are two versions of the chain rule. We're going to look at the first version in this video, right? So let me kind of set it up and then I'll state it formally as the theorem after we see the general pattern. And the idea is this. Let's say you have one function, like y is a function of u. But then let's say that your u is a function of x, right? So in other words, y depends on u depends on x. So ultimately, right, y depends on x. In other words, look at it this way. If I change my x value, I will likely change my u value. And if I change my u value, I will likely change my y value. I say likely because what if these are constant functions, right? So if they're constant functions, then they're not going to change. But in general, if I change this x, it will change u. And if I change u, it will change y. And then the whole idea of how are so for instance, how does the rate of change of u, right, affect or is affected by x, and then how does the rate of change of u affects y? So how are those rates of change related, right? Well, let's write down two equations. So let's say we took the derivative of y with respect to u. So and let's use our d notation for this. The d notation is really helpful for seeing at least intuitively where this pattern comes from, right? So we have it like this. So this is f prime of u. And then we have du would be with respect to x, since that's the variable that directly affects u. And then I'll write this as g prime of x, right? So my question, what we would like to figure out now is what would the derivative of y with respect to x be, right? You know, like how could I get dy dx out of these two equations? Because that's my goal, right? My goal is if I were to, and this is what I'll write down in a second, if I were to plug my u into here and have y equals f of g of x, right? What would its derivative look like? Well, if you look closely at this expression and this expression, they have something that at least points to why this rule makes sense. They have a du in the denominator here, and they have a du in the numerator here. So it seems at least plausible, right? It seems plausible that if we were to multiply these two things, the dy over du and the du over dx, which really is just a notation at this point, right? But it seems plausible that if we multiply these two, then the dus would, for lack of a better word, cancel out, right? Or we could somehow reduce the product to just dy over dx. So again, it looks like if I take dy over du and multiply it by du over dx, it seems, again, if we're allowed to cancel these things, right, then it seems like we're going to end up with what we want, dy dx. And this is the intuition, and that's all it is at this point. We don't have the machinery or the background to get super precise here. But it seems, at least intuitively, that if we multiply these two separate derivatives, dy du, du dx, then the du's will cancel and we'll be left with dy dx, right? So that's the first version of the chain rule. So let's go ahead and state this as a theorem, right? And it is the chain rule, but really I like to call it the composite rule, because all the other rules are named after operations that you do: multiple, sum, difference, product, quotient. The chain isn't really an operation per se, but composition is. So I like to call it the composite rule, or the in lieu of the chain rule. And then this is version 1. Right? Well, let's see what it says. So again, even with how it's stated, I'm going to state it kind of somewhat informally. I'm just going to say, assuming that f is a differentiable function and g is a differentiable function on some suitable domain, then the composite will be differentiable, right? So if y equals f of u and u equals g of x are differentiable, right, on some appropriate interval, right? And again, I'm not going to get into the details of what that means. It's a bit technical, but we'll just say on some appropriate interval, then the composite itself is differentiable. Then y equals f. So if I literally take the g equation here and replace u here, so then f of g of x is differentiable, again, on some appropriate interval. So is differentiable, and we have a formula for the derivative. We're going to take this approach and say that dy dx of this function can be written as the product of this derivative, so dy du, and this derivative, or the derivative of this function, I should say, du dx, right? And yeah, so that's what it looks like, and well, that's what the theorem looks like. Let's see what it looks like in practice, and we'll do a few examples here just so you get a sense of it. One, so you can recognize when you see a composite, and then two, how to actually compute the derivative. Now, the first example that I'm going to do can be done multiple ways, and I'm going to do it 2 ways just to show that it works out the same. So let's say we have the function y equals 4x plus 3 all squared, right? So let's say that's the function, right? So because the 2 is not a very big power, right? We can FOIL this out. So let's do it without using this new composite approach, right? Let's say we realize, hey, I can write this as, if I wanted to, I could write it as a product and use the product rule. That would work. But then I realized, hey, I could FOIL it out and even get rid of the product of these two functions. So if I FOIL this out, I will have 16x squared plus 24x plus 9, right? Yeah, so if I just use a bit of algebra, right, I can reduce it to a problem where it's the very basic of rules that I have to apply. So in this case, dy dx is equal to, now look, I'm looking at this expression here, this form of the function on the right. This is going to be 32x plus 24, right? Not a bad derivative, right? Here's an alternative way, though, just to illustrate the whole composite approach, right? So, or, notice we have, I guess you could say there are three operations here. You're multiplying, you're adding, and then you're doing a power, right? But for instance, if I just put a placeholder here, in fact, if I let u be equal to 4x plus 3, then I can write it in the form of this theorem, where I could literally write y as a function of u and u as a function of x. So I can identify the two types of functions that are composed in order to give me this function, right? And that's the first step in using this first version of the chain rule. You have to recognize the composite, right? And some of them are going to be, they're going to be as plain as day. Others you have to look a little bit more closely. But if we let u equals 4x plus 3, now the 4x plus 3, it is sometimes referred to as the inner function. And those are the operations that you would perform first, right? So in other words, you have a linear function here, but then that linear function is being raised to a power. So if we let the linear part be our u, then it means I can rewrite y in terms of u and just put that y is equal to u squared. So instead of expressing this one function as a composite, I can show you the two pieces or the two different functions. Think of those, like I said, the assembly line. You would do this first, and then you'd pass it on to the person who's going to square. And if it needs to be passed on to something else, it will be passed on to something else, right? So again, think of this as the chain of all the operations that come together to make this one operation, right? But it's a function inside another function. That's why it's called the inner function. So this is sometimes called the inner function. It's not my favorite notation or connotation, but it's pretty popular. And then the power function is sometimes referred to the outer function, right? Okay, well, let's see what the theorem says. In fact, let me just scroll back up. It's right there. It says if I want to find the derivative of this function, one way I could do it is by differentiating the y function, which is this, differentiating the u function, which is this, and multiplying them together, right? Well, let's see what that looks like. So if I write down, so let's differentiate this one. This is, so du dx is just going to be 4, right? Because when you apply the power rule to this term, you bring the 1 down, you'll have 4 times x to the 0, which is 1, and then plus the derivative of my constant is 0. So that's du dx. Then let's write down dy du. Again, use the power rule. This time, bring the 2 down, keep the u, and subtract 1 from that power, so we have the power of 1. So the chain rule says my dy dx, my derivative, is equal to the product of these two things. So it's 4 times 2u. But this looks a little strange. Like on this side, we have the derivative, it says with respect to x, but yet on this side, we have it in terms of u. Right? But what we can do, since we know what u is, right, I can plug it back in right here and get my final answer in terms of x. So it would look like what I have right up here, right? So this would be 8 times u. But now this is where I do the composite again. Wherever there's a u, I replace it with 4x plus 3. So this is 8 times the quantity 4x plus 3. And if I distribute my constant, I'll get exactly what we got up here, the 32x plus 24. Right? So this particular function, this y equals the quantity 4x plus 3 squared, could be, we can find its derivative in lots of different ways. However, if I were to change this, instead of having a 2, let's look at this example. What if I had y equals the same 4x plus 3, but let's say I did it to the power 200, right? Then this approach up here doesn't seem too practical anymore. Are we going to write down 200 factors of 4x plus 3 and FOIL them out? I'll let you think about that for a second. I think I'll pass. Right? I think I'll pass. I don't even know if I could, where could I fit 200 factors of 4x plus 3, right? But it's still a composite. The only difference is just that now I have a slightly bigger power. But I know how to handle any kind of power. So my first step would be almost identical to what I did right here. I would still choose this part as like the first part of my chain, right? These are the first operations that I would have to do, right? I'd have to do the 4x and then plus 3, and until I figure that out, I can't do the 200. So I would let u be equal to 4x plus 3, and then once I do this, it means that my y function, like the next one now, is whatever, so it's just going to be my u raised to the 200, right? And then it allows us to write one function, one composite, in terms of like these two pieces. One piece is in terms of x, and then the other piece is in terms of u. And the chain rule says go ahead and differentiate these separately. So du dx is still 4. And then dy du, this is where it changes just a little bit. But the power rule, it no matter how big the power is, you still bring it down, and then you still subtract 1 to get the new power. And then the chain rule says, so therefore dy dx is the product of these two things. 4 times 200 u to the 199. I can multiply these two coefficients to get 800. And then wherever there's a u, to get my final answer, replace u with the 4x plus 3. So take this expression and plug it back in. And notice when you do that, you're forming another composite, right? It's another composite because you have 800, but now it's times this quantity, 4x plus 3, all to the 200th power. And it kind of makes sense that if the original function is written in terms of a composite, then the derivative should be in terms of a composite. And that's exactly what it is, right? Let's do just a couple more examples, not necessarily using these specific types of functions, but other types. Let's say you had your y is the fourth root of 3x cubed minus 4x squared plus 8x plus 10. Right? So let's say we had this as our function. Right? Well, again, knowing what I know about roots, I can write the fourth root as a fractional power. So 3x cubed minus 4x squared plus 8x plus 10, all to the 1/4 power, right? And there is the composite. In order for me to evaluate this function, I would have to first evaluate this third degree polynomial, and after, and only after that is done, then I would take my fourth root, right? And if you think about the process or the order in which you would do these operations, it pretty much tells you what the quote-unquote inner function is. So in this case, I'm going to let u be everything in the parentheses here. So 3x cubed minus 4x squared plus 8x plus 10. Once I do that, it allows what it does by doing this and writing u as a separate equation, it allows me to write down the y equation in a more simpler form. But the trade-off is now there's this third variable, this u, right? So again, this process, this first version of the chain rule, it allows me to write a composite, right, function as two simpler separate functions. And it says go ahead and differentiate this one by itself, go and differentiate this one by itself, and the way you put them together is through that product, that special product, right? So let's write down du dx. This is going to be 9x squared minus 8x plus 8, right? And then let's write down dy du. So dy du, well, using our power rule again, this is going to be 1/4 times u to the negative 3/4. But let's go ahead and rewrite it so that I don't have a negative exponent. So I take the reciprocal. I already have a 4 in the denominator, so the 4 is still in the denominator. Now the u to the 3/4 is also in the denominator. And then, so the chain rule says to find the derivative of y in terms of x, I multiply these two, right? So that's my next step. And it's also, it's also very important that we label things correctly. Like, starting with the original function, how we label what is u, what is y in terms of u, and then the fact that now at the end we're finding the derivative in terms of x. So there are lots of variables to keep track of, and that's why it's important that we label things correctly. Right? So we're going to take this derivative and multiply this derivative. So I'll put the 1 over 4u to the 3/4. Now, since I have a fraction here, I'm going to put this over 1, and then I see what happens in the numerator. I multiply these two, and what happens in the denominator, I multiply these two. So in the top, I will have 9x squared minus 8x plus 8, and it's all over. I have my 4. And now, wherever there's a u, I have to plug this long expression back in, right? The 3x cubed minus 4x squared plus 8x plus 10, and that's all to the 3/4 power, right? Now, I'm gonna write the final answer in one alternative form, just so you can see what it looks like if I were to go back and write this as a root. So here is the derivative of our original function in terms of x. So in the numerator, we'll have the 9x squared minus 8x plus 8. in the denominator we'll have a 4 times, and the 3/4 exponent is telling me to take the 4th root of this whole thing raised to the 3rd power. So I'm going to need a big radical here, but that is the 4th root, and then I'll have of the quantity 3x cubed minus 4x squared plus 8x plus 10 all to the 3rd power, right? So let me just scroll back up. There was the original function, and then here is its derivative, right? And what happens is, as the functions become more and more complicated, then the derivative tends to follow suit, right? Let's do one more example. Let's look at something that has like our special e, but not just e to the x anymore. So this is our 4th and final example. Let's say we have something like e to the x squared minus 3x plus 1, right? So this whole quadratic is in the exponent. So it's not just e to the x anymore, but it's e raised to yet another function, right? With the e, you have to, you don't see the parentheses the way you see it, like, something raised to a particular power, or a root like we did over here, right? You don't really see it. It's unfortunate that at this level we tend to use this notation exclusively for the exponential function, but there are other books there's software that utilizes this notation for exp, and then they put what's in the exponent actually in parentheses. So then it gives you a clearer idea of the inner, like what's inside, right? Again, if I ask you to evaluate this, you'd have to figure out what number is in the exponent first before you do the e, right? You can't do the e until you've figured out what x squared minus 3x plus 1 is. If I give you x equals 2, you have to figure out that part first before you do e raised to that particular power. So the reason I like this notation, I'm not saying you have to use it, but it's on par with things like the sine of, like x squared, or the ln of x squared, and so forth. So it gives you the sense of the composite more clearly, right? But again, it's just another way for you to make sense of when this special operation is performed. All right, so let's see how we would do this. So think about the functions that I currently know how to differentiate. I can differentiate polynomials by themselves. I can differentiate the e to the x by itself, right? Now we're trying to see how can we differentiate them together, not as a product, not as a quotient, not as a sum, not as a difference, nothing like that, but in terms of this composite. Well, since I know how to differentiate the e by itself, I am going to let u be the entire exponent. So if I let u be equal to x squared minus 3x plus 1, that means my y equation becomes e to the u. And I have a rule, or I have rules that tell me how to differentiate this. I have a rule that tells me how to differentiate the basic exponential function. So when I differentiate u with respect to x, I will get the familiar 2x minus 3. And then when I think about my rule for the, what I call the natural exponential function, if I differentiate y with respect to u, I get back the e to the u. Because remember, the derivative of e to the x is the same as e to the x, right? It's its own derivative. So I can differentiate these equations separately. Now I have to be able to put it together and write down what dy dx is for our original function. And that's where the chain rule comes in. It says that dy dx can be written as this times this. So the quantity 2x minus 3 times e to the u. But again, we want our final answer in terms of x. A simple explanation as to why is because our original function was in terms of x, right? So if we're writing down the derivative, we want it to be in terms of whatever letter or variable was used originally, right? And then again, I'm using parentheses here because I'm multiplying by a binomial. So then I end up getting 2x minus 3 times the quantity, and then I have e. But instead of writing e to the u, I go back and I form my composite. I take that function and I plug it back in there, and I get e to the x squared minus 3x plus 1. So overall, this first version of the chain rule, I don't think, like, the process itself isn't overly complicated, but I think it's the concept, like knowing when you need to do it, being able to recognize the composite. That's the key skill here. The rest of it is important. Don't get me wrong. I'm not saying that all of this isn't important. But if you don't recognize when you need it, then you won't know when to do this, right? So then this becomes redundant. So it's important to recognize when you have a composite and then follow this particular process. Or there's a second version to the chain rule, which essentially takes what we've done here, and that version requires, again, even a little bit more insight to where you don't write them as separate equations, but you can essentially skip the middle part here and go to the end result. So that method doesn't involve u at all, right? The letter u. Everything is kept in terms of x to the point where you can start to look at the original function and just write down what the derivative is. But it has to be with a composite. All right, so we'll see that in our next video. See you then.